Hello, good morning. Myself Navneet Jain, lecturer in electrical engineering in electronics department here in Government Ramchandra Khitan Polytechnic College, Jaipur. I teach subject circuit analysis EL202 for second year electronics students. Today I deliver a lecture on parallel resonance in RLC circuits. So this is RLC circuit, a voltage source and parallel resistance, inductance and capacitance. So this is parallel circuit of AC and this is resonance condition of parallel circuit. The phasor diagram is shown here. In this diagram it is shown that current through resistance, the phasor diagram, current and voltage both are in same phase. The resonance curve is shown here. Fr is resonance frequency and I is the current. The graph is between current and frequency. At resonance frequency Fr, the current I is minimum. Just below this Fr, the circuit is inductive and after that circuit is capacitive. Next is characteristics of parallel resonance. In parallel resonance, there are some important points. The applied voltage and resulting current both are in same phase. The power factor of the circuit is unity. At resonance, impedance is maximum and current is minimum. It acts as current amplifier. Next, fifth point, below resistance Fr, the circuit is inductive, as I discussed earlier. Next is above Fr, the circuit is capacitive. Some expressions of parallel resonance. Condition for resonance. Resonance occurs when BL equal to BC, means susceptance of inductor is equal to the susceptance of capacitor. Frequency for resonance means resonance frequency for parallel circuit is given by Fr equal to 1 upon 2 pi under root 1 upon LC minus RL square upon L square. Next expression is of impedance at resonance. Impedance at resonance equal to Z0, this equal to L upon RC. And similarly, admittance Y is reciprocal of impedance, as we know. Y means admittance equal to 1 upon R plus J into omega C minus 1 upon omega L. Current at resonance IR equal to VRC upon L. Now voltage drop across inductance VL equal to I into 2 pi FRL. Here F equal to FR. Voltage drop across capacitance C VC equal to I into 1 upon 2 pi FRC. Again F equal to FR. Voltage drop across R, this is equal to VR equal to IR. Now Q factor Q equal to R under root C by L or equal to R upon 2 pi FRL or equal to 2 pi FR RC. Power factor at resonance. Power factor as resonance is 1, means cos phi equal to 1. Unity power factor. Expression of bandwidth in terms of Q. Bandwidth equal to FR upon Q. Now some problems related with parallel resonance. Problem number 1, it is here. in circuit. This is parallel RLC circuit. Capacitance in parallel with inductance and resistance in series. So this is the circuit for the parallel resonant circuit shown below. The value of resonant frequency is, there are four options: A 1.25 megahertz, B 2.5 megahertz, C 5 megahertz, D is 1.5 megahertz. The right answer is A. The explanation, as the formula we know, the resonant frequency Fr equal to 1 upon 2 pi under root LC. We put all these values, means inductance and capacitance. We get 1 upon 6.28 under root 100 into 10 raised to power minus 6 into 162.11 into 10 raised to the power minus 12. We altogether get 1.25 megahertz. This is the right answer, A, 1.25 megahertz. Now next problem. For the parallel resonant circuit given below, the value of the inductive and capacitive reactance is what? The circuit is given, the voltage VA equal to 10 volts, capacitance value is 162.11 picofarad, inductance value is 100 microhenry, resistance value is 7.85 ohms. So what will be the value of inductive and capacitive reactance? A, B, C, D. Four options are here. So right option is, answer is C. Explanation: resonant frequency, as we know, Fr equal to 1 upon 2 pi under root LC. We put the values, this equal to 1.6.28 into 100 into 10 raised to power minus 6 into 162.11 into 10 raised to power minus 12. Thus we get the value 1.25 megahertz is the value of resonant frequency. By having resonant frequency, we can find out inductive and capacitive reactance. Inductive reactance XL equal to 2 pi F into L. So put the value of 2 pi F into L, we get 785.394 ohms. This is inductive reactance. And capacitive reactance, as we know the formula, XC equal to 1 upon 2 pi FC. Put the values of F and C, we get 785.417 ohm. So inductive reactance is 785.394 ohms and capacitive reactance is 785.417. Almost both are equal. As we know, resonance frequency, at resonance frequency, inductive reactance and capacitive reactance both are equal. So this is verified, that this is the resonant circuit and resonance frequency is 1.25 megahertz. The answer C is justified. Question number 3. For a parallel RLC circuit, the incorrect statement among the following is. Which one is the incorrect statement? First is A. The bandwidth of the circuit decreases if R is increased. B. The bandwidth of the circuit remains same if L is increased. C. At resonance, input impedance is a real quantity. D. At resonance, the magnitude of input impedance attains its minimum value. So answer is, which one is incorrect? The explanation is here. The answer D. Answer is D. Explanation is that bandwidth equal to 1 upon RC. It is clear that the bandwidth of a parallel RC circuit is independent of L and decrease if R is increased. At resonance, imaginary part of input impedance is 0. Hence, at resonance, input impedance is a real quantity. In parallel RLC circuit, the admittance is minimum at resonance. Hence, the magnitude of input impedance attains its maximum value at resonance. So, answer D is justified. Thanks.